I hope. All right, hi everyone. My name is Brandon Dail, and I am a developer at Facebook. And then today, unfortunately, I have to talk about React after Rich's talk there, though. Hopefully, kind of put me in a spot there. But what I'm going to be talking about are these things right here: algebraic effects, fibers, and coroutines. And first off, I want to thank you for coming to a talk that has a title like that. That's very, very brave of you. So the concepts here, these are all something that you might have maybe encountered, some of these words like on Twitter, but you might see some thought leaders throwing these things around pretty often. But these are really sort of academic concepts, and what I want to do is really talk about these ideas as academic concepts, how they relate to React, and how they relate to some of the recent work that the React team has been doing. And so all of the things that we're going to discuss today, all of the concepts aren't necessarily new or novel with React. They're ideas that have already existed in other parts of the programming community and the computer science community, but these ideas have influenced the direction that React has taken, and the adaptation of these ideas in the context of UI library is itself potentially novel, but at the very least hopefully interesting. So I know that academia, computer science has kind of a scary reputation, so I want to follow React's lead here and give you a helpful warning a little bit ahead of time, and that is, warning, this is just for fun, so you don't have to know what any of this is to actually use React. So the concepts that we cover today are going to be sort of mostly internal, things that are hopefully opaque to most product developers. So you don't have to know what an algebraic effect or coroutine is to use like React 17 when it comes out, don't worry. And it won't necessarily make it easier to build React applications, but understanding these ideas will hopefully give you a better mental model of what React actually is nowadays, which can be, I think, helpful in a lot of contexts. All right, so all of this is related to this project called React Fiber. Who's heard of React Fiber? Yeah, okay, cool. So what exactly is React Fiber? It's kind of a cool code name, but doesn't really give us a lot. So React Fiber was a relatively recent effort made by the React team to rewrite React from the ground up while maintaining full backwards compatibility. It was released back in React 16, which was released quite a while ago now. And so if you're hopefully using that version, then you've been using it for a while now. And hopefully it's been so good that you didn't even really notice that React was rewritten. Which always reminds me of this quote: when you do things right, people won't be sure you've done anything at all. I think this is the goal for a project rewrite. All right, so let's try to understand some of the motivations behind React Fiber, because rewriting your mission critical infrastructure for no reason is usually a bad idea, and doing it in any case is usually a hard sell for management. So there has to be some significant advantage that Fiber provides over the previous implementation of React. And there are a lot of really good reasons, but the ones that I'm going to be focusing on most today are something called concurrent rendering. So have you guys heard of this before? Maybe sounds a little familiar. So this is the same thing that Rich was talking about, but I want to talk about it in a little bit broader of a context. So concurrent rendering, which was formerly known as like async rendering, is a sort of general term that currently refers to primarily two features that React enables. There's time slicing, which we saw a little bit of, but it actually involves a little bit more, and the other major thing is suspense. Who's heard of suspense? Cool. So I want to preface this by saying that both of these may involve some new or updated APIs in the future for actually utilizing them to the sort of fullest extent, but I don't really want to talk about how to use them. I really want to just talk about the idea, not the implementation. So, besides the fact that both of these names are really cool, what do we really know about them? Let's dive into time slicing, which thankfully we don't have to spend too much time on because we just heard about it like 5 minutes ago. So time slicing really is this idea. And if we take a quick step back, we know, browsers themselves are responsible for things like, executing your JavaScript, layout, painting, all that kind of stuff. And we usually want to do that in 60 frames per second, right? And if we do the math on that, that means we have about 16.67 milliseconds to do everything that we need to do. And if the browser has to do more work than about that time, we get what we call jank, which we saw in Rich's example a second ago, where things start to stutter and generally lag, and that's a pretty terrible user experience. And time slicing, what it is a way to take all that work that React has to do and sort of slice it up into the smaller chunks over those 16 millisecond timeframes, which lets React keep the application responsive. I'm glad I didn't put a demo here because we just got one. Thank you, Rich. But not only can React use time slicing to split up that expensive work over that time, it can also reprioritize different things to make sure that the page stays interactive. So, imagine a page with a long list of filtered items, and as you type in, that list of items updates, and if rendering that list is expensive, you might see that stutter that we saw. And so with time slicing, what we can do is take that expensive work, identify more important work, like rendering that text input, and prioritize that over the less important work of rendering things off screen or below that, we can delay with, out hurting the user experience too bad. So that's time slicing in a nutshell. The other feature is suspense. And suspense is a little bit harder to explain because it's kind of a more generic feature that solves a broader set of problems. At its core, you can think of suspense as a generic way for any component anywhere in the application to pause or suspend rendering if it requires some asynchronous data to render. And this can be anything all, like an API response, an asset like an image, maybe even another component if you're doing code splitting. So when a component suspends, it's essentially telling React like, hey, I know you really want to render right now, but I have to go get this data, so could you just put it on hold for a second while I do that? And that's, of course, a simplification, but hopefully it demonstrates the one aspect of suspense that we really want to focus on, which is that it involves interrupting React and then resuming that render asynchronously at some time in the future. And if we look at time slicing and we look at suspense, we can identify a single common requirement to make all of this work. And that's interrupting, or interruption. React has to be able to stop what it's doing, interrupt everything that's happening, and then resume that later on. Whether it means interrupting a render to spread it out over, multiple frames, or interrupting it to wait for some asynchronous data, being able to stop what it's doing and resume that later is a critical requirement for this concurrent rendering project. So we know what we need to make concurrent rendering work, right? But why exactly do we need React Fiber for that? Maybe why couldn't we just add a few lines of code to the old version of React, wrap it up with some set timeouts or something like that, and then, call it a day? There's some good reasons, and mainly to answer this, what we need to do is kind of take a step back here and talk about JavaScript for a second, because that's going to give us our answer of like why that's not as easy as, easier said than done. And I specifically want to talk about how JavaScript manages the work that it's responsible for doing. And to do that, I want to define what I mean by work really quickly, because that might not be obvious. So with React, the work that it has to do is things like creating DOM nodes, calling render, other lifecycle methods, the whole process of reconciliation, right? Everything that we would say is the responsibility of the React library. Now with JavaScript, we just define work as like the stuff that JavaScript has to do, the stuff that the engine or the runtime is responsible for. And that's things like creating variables, updating arrays, control flow, anything like that, basically executing your program, right? And in React, we think of components as like a unit of work, right? If we were to break it up into discernible components or units. It's an abstraction that defines some set of work that React has to do. And in JavaScript, we can define functions as a unit of work because a function represents some set of code that the runtime needs to execute. And how does JavaScript manage this work? How does it keep track of what it needs to do? Like most programming languages, JavaScript uses something called a call stack. And the call stack is this stack data structure, like a stack of plates, and it's used to track what function is being executed at any given time. So when a function is called, it creates what's called a stack frame, which you can think of as like an internal object in the runtime that represents that particular function call. And the stack frame usually stores information like the parameters that the function was called with, some local variables that were maybe declared inside the function, and other metadata about the function itself. As a program executes, functions call other functions, and the call stack keeps growing. Once a function is done executing, its stack frame gets removed from the stack, and then execution continues from the return address of that stack frame, which points to wherever that function was called from. So since this is a really critical concept for understanding what React Fiber is, I want to walk through like a really quick example just to make sure that we're solid on this. So this is a super fun little app here. We have a function add that adds two numbers, double that uses add to double a number, print double that just doubles and prints it. And then on line 13, we call this print double function with the number 5. So before the program starts at all, the call stack is empty. There's nothing in there. And then it hits that line 13, sees that there's a function call for print double, and then it creates a stack frame for that function call and pushes it onto the stack. After that, once it's inside print double, it sees, oh, double is being called, and then another stack frame for that function is added to the stack as well. And then this continues as double calls add, and then inside add, there's no more function calls. It returns a value. So no new stack frame is added, and control is returned to the previous call site. So that's going to be inside here. So that stack frame is then removed from the stack, and then we start this unwinding process where the same thing happens for double. And then we console.log, so that's a function call, adds another stack frame. We reach the end of print double, we reach the end of our program, and then the call stack is empty. So let's zoom in on what exactly is a stack frame, like what it might look like. So this is a simplified view of what you might see if you were to peek into a JavaScript engine. Like we said, a stack frame just stores basic information about a function call that it represents. So that we can see like this frame-specific data, like its parameters, local variables. And now here, I've represented the stack frame as this like JavaScript object, but it's actually really important to note that stack frames aren't things that you can access or use in JavaScript. You can't control them. They're completely internal representations in the JavaScript engine themselves and are created and managed implicitly as our program executes. So there's no way for the JavaScript program itself to access or use these stack frames. But why does that matter? Why do we care about call stacks or stack frames when we're trying to understand React Fiber? Well, the reason that it's relevant is because this model is actually pretty problematic and in tension with the goals of concurrent rendering. With concurrent rendering, we know that we want to be able to quickly interrupt what we're doing. And if we're relying on the call stack to track all of our program state, then we don't really have that ability to just stop the work that we're doing on demand. If we're nearing the end of that frame deadline, that 16 or so milliseconds, and the call stack still has a bunch of stack frames, we have to just wait for all of those function calls to finish before the browser can do things like updating the page layout or style. And before React Fiber, the implementation of React uses sort of like a recursive approach where when you hit a component, it would render it and then recursively do the same using this call stack to go down all the way to the bottom of the React tree. And since we can't access the call stack or stack frames from JavaScript, there's really nothing that we can do about that problem unless we look for an alternative execution model. And that's exactly what React Fiber is. So we can think of React Fiber as essentially a React call stack. It's like a React-specific implementation of a call stack-like model where React has full control over scheduling what work should be done. And if you can think of a fiber as a stack frame for a React component. So just like how a stack frame represents a specific instance of a function call, and stores information like the parameters, return address, local variables. A fiber represents the same thing but for React components. Instead of parameters, we have props. Instead of local variables, we have state. And instead of a return address, we have the parent component. In reality, it's really not much more complex than that. This is the some code that I pulled directly from the React source. This is exactly how React models a fiber internally. We have this like fiber node constructor function, which is just like a class. And you can see that it just sets some basic fields that stores information about the component itself. Things like its type, its return or parent, prop, state, key. And there's a lot more fields that I've excluded, but this is the basic idea. A fiber is just this representation of the component instance, just like the stack frame is a representation of the function call. But the key difference here is that unlike stack frames, fibers are just regular JavaScript objects. React can create them, manage them, delete them, manipulate them in whatever way it needs to. Now, it would be kind of silly if maybe it was just a one-to-one implementation with that, little advantage. But you might have also noticed that in this fiber node constructor, not only does it store information like about the parent, but it also has pointers to things like its siblings and its child. And this is in contrast with stack frames where you only have a return address. There's only one place that you can go once a function stops executing. And this is a small but actually a really powerful detail that makes fibers even more powerful. Since React doesn't have to rely on the call stack for keeping track of what it's doing, it has its own scheduler. And this scheduler can implement much more complex React-specific patterns that the native call stack can't represent. And the scheduler is responsible for knowing which fiber is being worked on at any given point, which one it should work on next, and if execution needs to be interrupted, it's also responsible for making sure that the work it was doing gets resumed correctly afterwards. And since a fiber stores more information like the children and its siblings, the scheduler can also make more intelligent and complex decisions around what work should be done and when. And unlike stack frames, fibers can actually keep around local data, like state, even if they're not currently active. With functions, once the function is done executing, anything that was local to that function, like local variables, is gone. And that's not the case with fibers. So if React gets interrupted while rendering, it can resume rendering that fiber with very minimal overhead. Almost all of the work that it has done can be preserved, which makes interrupting resuming a relatively cheap process. And unlike the call stack, when the scheduler finishes rendering a specific fiber, it can continue rendering from any other point. Right? With the call stack, it has to go back to that return address, that place that called the function. There's a single place that it can go, but the scheduler can prioritize other updates that occur in totally separate parts of the application. That's why we saw in the demo, when you typed into the input, it was able to update that immediately, even though there was already other pending work, like updating those graphs that had to be completed. And this is what enables React to prioritize those interactive updates. Okay, so we described fibers in the context of React, but what exactly are they? Did React invent these? What's the deal? Our goal here is to discuss these sort of as formal concepts, and how does fibers fit into that? Well, fibers aren't really a new thing at all, and React definitely didn't invent them. A fiber is this generic way to model program execution in a way where each individual unit of work, in our case components, works together cooperatively. And you can think of fibers as something in the same category as threads or processes, if that helps you, but all you have to know is that fiber is all about modeling some kind of program in a cooperative way. And this hopefully makes sense if you think about how we just described fibers in React. React can switch between fibers as much as it needs to because they're cooperative. No single fiber attempts to dominate the entire program, which isn't the case for functions, right? You can have a function that, maybe does a million recursive calls and brings everything else to a halt. And fibers are actually also used in a couple other high priority systems. So for example, Microsoft Windows uses them internally, and the OCaml programming language has used them for its concurrency model. So the fibers that React uses aren't exactly the same as these, but the idea is consistent. Now, coroutine is another term that I had in the title, and thankfully it's super easy now to define because it's essentially the same idea that we just laid out in fibers. Coroutines and fibers both refer to this same cooperative execution model. So a simple definition is coroutines and fibers are mostly the same thing. Now, even in academic computer science, the distinction between fibers and coroutines is blurry at best. If anything, it might be said that fibers are usually used to describe these low-level program execution things, while coroutines are something you see as a language feature, just like a function. But in the context of React, that distinction doesn't really matter, so we don't really lose much by simplifying it. Right, so we know what fibers are now, and we know what they represent, but what can we really do with them? What else does this enable? We know that they allow React to directly control this program state and the execution, which enables features like time slicing and suspense. And I want to say there's actually probably even more that this enables beyond that we're working on currently. But that's not the only thing that fibers enable now. Because React has this low-level control, it can implement more advanced programming patterns that wouldn't be possible in relying on the native call stack. And one of those patterns is something called algebraic effects. Ooh, scary. So algebraic effects are like an active area of research in academia, and they don't really exist yet in many production-level programming languages. They definitely don't exist in JavaScript, which makes it a little hard to describe them in this context. But we do have something that is relatively close that can give us a general idea of what they are. And that's error handling. So let's talk about how we manage errors and error handling in JavaScript. Hopefully we're all managing our errors. And hopefully most of this will be pretty familiar. So in JavaScript, error handling has two main parts, right? You have triggering an error and then you have handling that error. To trigger an error, we use the throw keyword. You don't have to import it, right? It's always in scope. It's a global feature. It's part of the language that you can use to indicate that at any time some kind of exception has occurred. Now, throw doesn't actually dictate what your program should do as a result of that error. All throw does is signal that an exception has occurred of some type. And that's when catch comes in. Catch, as part of a try-catch block, is what defines the program behavior for when an error occurs. And the resulting behavior of that thrown error is, so the same error thrown in different parts of the program might result in different behavior. And that's one of the main insights that I want to drive home. The act of throwing an error and the resulting behavior are totally independent. And if we think about it, this pattern is really nice, right? It's really easy to use. All the complexity of error handling is isolated into these catch blocks, and we only need this one API throw for all the possible kinds of errors in our program. Plus, it doesn't really matter how deeply nested throw is in relation to that catch block. It will totally bypass that call stack that we looked at earlier, and it will just work. So this means that any module, including third-party ones that you install from NPM, can throw errors, and they don't have to really worry about the specific details of how those errors affect program execution. So let's try to run with this pattern a little bit and see how it works with a couple other problems. So logging is a pretty common problem. Let's take a look at that one. We all probably have our own abstractions and interfaces for logging in programs and third-party packages that might require it. Maybe there's some package-specific API for configuring it or enabling it. But what if we took the same error, the pattern that error handling uses, and applied it there? So what if instead of having to manually import or configure logging, what if there was a keyword called log that worked just like throw? And just like catch, we had something like handle log. I couldn't think of a better name. That could catch or handle the log event and control exactly what kind of logging occurred. So now just like with error handling, any code that needs to signal that a log event should occur, it just leaves it up to the surrounding context to determine what exactly should happen. And unlike errors, maybe what if the program could even keep executing after that log event was thrown or triggered, like after a function call finishes? No importing, no configuring, it just works everywhere for everyone. That sounds pretty nice to me. So what about this with another problem, like network requests? What if we had a fetch keyword that allowed us to signal that a network request should occur, and then a handle fetch block that defined what should happen when the fetch was triggered? So the fetch keyword doesn't actually create the network request, it just signals that a request should be made, just like how throw signals that an exception has occurred. And maybe that handle fetch block could actually asynchronously return some data back to the code that triggered the fetch. And so not only does it keep executing after that happened, it actually reads data back similar to how a function call works. So hopefully these kind of demonstrate a consistent pattern that we could maybe apply to a bunch of different effectual problems, things that involve side effects. And this pattern is essentially what algebraic effects are. The name is really a lot more complicated than the idea, and all of the examples that we just discussed demonstrate the core concept of what algebraic effects are. They're composed of these two parts, effects and effect handlers. So effects signal to the surrounding environment that some kind of event or effect has occurred and needs to be handled. So this is just like when throw, it signals that an error event has occurred. And then we have effect handlers, which allows you to run code in response to these effects, and even potentially return some value. So in the case of try catch, we can't actually return a value from catch, right? We can't even keep executing the code that is thrown. But with real algebraic effects in a language that would support them, the effect handler could potentially pass some data back. And maybe even do that either synchronously or asynchronously, which is a really powerful detail. And what that means is that languages that have algebraic effects don't need things like iterators or async await or generators, because all of those can be built on top of effects. They can be implemented in user space. And effects, just like throw and catch, can be nested at any level in relation to the effect handler. So in our examples with like logging and fetch, it only showed one level of nesting. But really it works just like throw and catch, where throw can be 1 or 100 function calls deep, and that catch block will still handle it. And that's really the core idea of algebraic effects and effect handlers. They allow us to model effectual behavior, like errors, logging, or network requests, where the effect and its behavior are independent. So how does this tie back to React? We know that fibers allow React to implement these more complex patterns like algebraic effects, even though they don't exist in JavaScript. So if that's the case, in what way has React implemented them? How is it relevant? And it's relevant because we can actually think of React Suspense in terms of algebraic effects. And this is probably where you've heard this term most, if you've ever heard of it. To recap, Suspense is a way for components, React components, to signal to React that it doesn't have some async data that it needs, and that it needs to suspend. And React has to potentially pause what it's doing, wait for that, and then resume later on. So I want to sort of ground this in a real-world example, because it's a little easier to understand how this relates to algebraic effects if we know what this actually looks like. So fair warning, this is like experimental API. It probably doesn't look like this when it'll be officially released, so don't get too caught up on the specifics here. We just want to use this to demonstrate the core idea. So here we have a very simple example of using Suspense to render some async data. Specifically, we have this user component that fetches some data for a user and then renders the h3 tag with their name. So we have a couple of functions, create cache, create resource. We just assume that this comes from like some unknown data caching library that works with React Suspense. Don't worry about it. Just they assume they exist and they work. So we create this cache, and then we create this something called like a resource. And we can think of this resource as like the concrete interface for how our component will fetch that data in a way that's compatible with Suspense. So we pass it this fetch user value, which we will assume is a function that like fetches a user and returns a promise with the data. And the most important part is here. When the user component renders, so this is inside the body of the component, we call this read method on the user resource. We pass it that cache and the ID for the user we want to fetch, and then you can see here that we just assume that the result is returned synchronously, even though we know that this is actually async data. So what this does is if the user resource will check that cache that we provided, and if it has the data, then it will just render synchronously, and great. Everything is dandy and it renders. But if it doesn't, then that's when we'll actually trigger that suspend event and let React know that it should try to wait for the data. Now, React might listen and wait, or if it thinks it needs to render this component quickly to keep the page responsive, it might keep rendering and then render like a fallback, like a spinner or whatever you specify. So this user resource here just signals to React that a suspend event has occurred, and then it's up to React to decide what the behavior of that app should be. And hopefully that sounds a little familiar. You can think of Suspense as an algebraic effect. When this read function doesn't have the data that it needs, it signals to React that it should suspend rendering and wait for it. And we can think of this as a React-specific suspend effect, and React itself acts as the effect handler, deciding what it should do based on the information that it's received. And just like other algebraic effects, this suspend effect is contextual. So if you render the same component in two different parts of your application, the behavior of suspending may differ depending on how React's scheduler has prioritized things. But before we started talking about algebraic effects, we noted that they don't exist in JavaScript. So how does React actually implement this? Well, we can pull the curtain back and try to take a little peek. And this is code that I took from that unnamed caching library that I told you not to worry about. And this is just a small snippet of the source of that read method that is called inside the render of that user component. And I've excluded some of the stuff for brevity's sake, but we can see here that it's like a switch statement that's checking the status of some record. We can assume that this is a cache record for the data that we want to read. And you'll notice that in two scenarios, empty or pending, React actually ends up throwing something called suspender. And this is how React manages to implement suspense. When a component needs to suspend, the method throws a promise, which represents that async data that the component is waiting for, which might feel a little weird, I know. When it throws, rendering just stops, because as we mentioned with throwing an error, it just stops the program execution and continues from that nearest catch block. But if we're throwing when we're rendering and the program just totally stops, then like how does this component ever even get rendered? Wouldn't that just cause all of the work to be totally lost? And thanks to fibers, the answer is no. We said that fibers enable React to implement algebraic effects like this, and the reason for that is because it uses this technique of throwing to fake algebraic effects. And that technique isn't problematic because React relies on fibers, not the native call stack, to track program execution. So when that throw occurs and rendering gets interrupted and the call stack gets unwound, React can resume again without really losing any work, and there's very minimal overhead. It might even render and throw again a handful of times while that promise is being resolved, but eventually, hopefully, it will resolve and the component can render without suspending. Another really quick example of how algebraic effects have influenced the React API is hooks. So one thing, hooks don't throw promises or anything like that. Don't worry about that. Suspense is unique in that way. But they're modeled in a very similar way to algebraic effects. And I think these have been brought up a few times, so hopefully they're a little familiar by now. But for those of you who haven't had the chance to use hooks, the gist of it is that you have, instead of creating like class components and doing things like set state on the this or stuff like that, you can use these special functions called hooks that hook directly into the React runtime, and they're kind of magical. So here this is a simple like counter component that renders a button with a number in it, and when that button is clicked, the number gets incremented. And the state for that counter number is defined using this use state hook, which you import from React. Unlike other functions, that state value will persist between the render calls, and that kind of calls back to the fact that we're using these fibers to represent and track that state, which persist things between renders. And you can think of useState as like a state effect. The value returned from useState is dependent on the context of that specific instance. Much like how with errors, the behavior of the error is dependent on the surrounding catch block. And interestingly enough, state is one of the first examples that you'll see if you look into the academic resources on algebraic effects. It's like the classic example of how you can use them. Now, in the case of hooks, they're actually kind of a limited example of algebraic effects because you can't define your own effect handler, right? Like you can with catch for errors. When you use state, you don't have any control over the value that's returned. It's directly coupled to React. But we might consider a potential future where maybe algebraic effects are integrated into the language itself, and we might imagine a case where stateful components can be reused across any front-end library because they all use a generic state effect, much like how any library can safely use throw and assume it will be handled. That'd be pretty cool. All right, so I covered a lot of ground, and a lot of that ground was pretty rough terrain, so let me just summarize a little bit of what we covered. React Fiber, as I said, it was an effort by the React team to rewrite React in a way that provided React this more low-level control over program execution. They accomplished this by using the existing idea from computer science called a fiber, which is a model of execution based on cooperation, which works really well with React's component model. By relying on fibers, React was able to implement APIs modeled after algebraic effects, which is a generic and useful way to model effectual behavior with effects and effect handlers. I know that's a lot to take in, but hopefully this sheds some light on what exactly React Fiber was, why it was useful, why it was necessary, and helps you understand the actual program model that React uses internally. And that's my talk. Thank you so much for listening.